Right, sounds good. So I'm sharing my screen. Can you guys see it? And can you guys hear me?
Yeah. All right. Yeah. Take it away.
All right, sounds good. Thanks, Aaron. So hi, everyone. I'm Joshua. I'm a grad student from University of Illinois. So today I'm very glad to talk about my work, feature extraction on synthetic black hole images with neural networks. So this work has been done with a couple of grad students and my collaborator, Charles Gammy, right here. So this is the first time during this brown bag launch, even though I don't have a brown bag with me, but I would like to take this time to introduce myself a little bit. So work on many projects. So one of the projects I'm working with Charles is machine learning applications for the Event Horizon telescopes. And I also work with Gil Holder, also at the University of Illinois on dark matter substructures in strong lensing, and also Xin Liu on using machine learning to estimate AGN black hole mass. So I have lots of interest in machine learning. So I'm interested in reinforcement learning for examples, but on the cosmology or astrophysics side, I'm interested in dark matter, neutrinos, supermassive black holes. And I'm graduating, I'm on the job market potential this fall. So if you're looking for postdoc, please definitely let me know. All right, so today's story begins with last year, the Event Horizon Telescope just announced that we have the first image of a supermassive black hole at the center of M87. So as an astrophysicist point of view, what we would like to understand is what kind of physics can we learn from this black hole image? So by saying physics, we mean some parameters right here. So in this talk, I'm going to focus on one parameters, which is black hole spin. Sorry. Are you guys still seeing my screen? Are you guys seeing the mailbox? Okay.
We see it.
All right, cool. So spin is one of the most interesting parameters of black hole in my personal opinion, because it actually changed the geometry of the space-time around the black holes. And it is also one of the three fundamental parameters that predicted by the no-hair theorem or the no-hair conjectures. So it's really interesting for us to learn about the spin of the black holes. And one of the questions we have right here is that, can we estimate the spin of a black hole from this image in a data-driven way? So by saying data-driven ways, what it means is that we have a theoretical model, and we use this theoretical model to build a lot of images and try to compare these theoretical built images with the real data and see how close they are. So by doing that, we're actually building a bunch of these simulations. So this is one of the simulations we built in University of Illinois. So we use IHUN 3D, which is GRMHD simulations to simulate a bunch of 3D structures of these black holes. And then we use IPOL, which is a radiative transfer code, to generate 2D image of these black holes. So on the left-hand side, it's a 4 resolutions of an image. And on the right-hand side, it's what the current Event Horizon Telescope would resolve on our synthetic data sets. And I think I cannot show the animations right here. Are you guys seeing any animations? Nope, sorry. So let's jump back to the pictures though. So this has been quite challenging in a data-driven way without like in a traditional way, because one thing we noticed that if you look at each rows of these black hole images, they actually have the same spin value, but all of them look very different. So the in-class variation is actually quite huge. If you just directly pick one of the image and you ask me what the spin is, even if you ask some of the experts, sometimes it's really hard for them to tell what the spin of a black hole just directly from one image. And to make it even worse, in this in this synthetic image I selected in the red box, these two look extremely similar, but actually have very different spin values. And to make it even worse, when you apply the burring on top of it, you can see on the right-hand part, they look almost exactly the same, but they have very different spin values. So as a traditional astrophysicist point of view, what we usually would do some chi-square analysis on top of it. And this usually wouldn't work. So then we need to come up with some other much more clever ways of using to do a data-driven ways on estimating spin values. So therefore, we turn our attention to one of the greatest tools in computer vision these days, the convolutional neural networks. So this is the neural network we use. It's called ResNet 18. It's a beautiful, compact convolutional network that was the state of the art a few years ago. It still works pretty well these days. So we modify the last layers of our neural network so it outputs the parameter of our interest in a continuous range, for example, like spin and the mass of black hole and also accretion rates. In this talk, I'm going to focus on spin only. And in our model, which includes both MAD and SANE, which have to do with how strong the magnetic flux is around the black holes. And we train on 100,000 of this image and validates on another 100,000 of these images. And to see how good our neural network performs, we actually build up 3 different blind data sets. So blind data set A on the top has the same spin value compared with the training set. And as you can see, I think the neural network is doing pretty well on estimating the full resolution data, which is the high resolution one. And for blind data set B, we actually change the plasma physics so that they have different electron temperature, for example. Right here, we actually see much more scatterings about the spin predictions right here, but the neural network are still doing a pretty good job on picking up the right spin value in most of the cases. So what makes us really exciting is that we have a blind data set C, which have a different spin value that have never been shown to a neural network. And we use a trained neural network to estimate the spin value on top of these blind data set Cs. And as you can see, that the distribution of the spin is actually heavily influenced by its prior, but the mean value of these distribution is actually pretty close to the ground truth, which we put in right here. So which means that the neural network are able to generalize and learn something really useful information about the spin value of the black holes. And I think it's doing amazingly well compared with the traditional chi-square method. So one of the questions my advisor, Charles gave me actually have is that how can it work so well? So this is the plot I showed to him. Like as someone who trained on neural network, usually just dump a lot of data into big pile of neural network and usually tweak some of the parameters and just suddenly works. But as a physicist point of view, this is not satisfying. So we really like to understand what the neural network learns. So what kind of features is learning that are related to the spin right here. So this is the example of how the inner structure of a convolutional neural network. So usually there's a convolutional layer applied on top of the input images. So usually you can see some convolution and a downsample compared with the input images that are generating new features. And the convolutional neural network, the convolution kernel is actually learned directly by training from the data. So in our ResNet architecture, there are basically 5 natural places for us to have these feature maps, and which are contained in the several basic blocks right here. And as you can see, because of the downsampling, when you go down to the basic block 4, usually it's really hard to interpret what the image really is. But when you go back to the first convolution layer, you can actually see that when you apply just one convolution kernel on the input image, it still looks pretty similar to the original input. And what really surprises us, or what really makes us exciting, is at the basic block 1 and basic block 2's feature maps. Because we realize that there's a lot of new features that are generated from the neural networks after the training. And it's also interpretable because we can still recognize the ring-like structures of the black holes right here. So we can use these feature maps to study what kind of new features that the neural network learn that have to do with the spin of the black holes. And so what I mean by learning new things is that we actually look into some of these feature maps with our trained ResNet and compare with an untrained ResNet. What I mean by untrained ResNet is we basically, untrained ResNet is actually a pre-trained neural network. If you know machine learning, that these are trained already with black cats and dogs images in the ImageNet data set. So it kind of know how to pick up the edges of an object but you have never seen a black hole in this neural network's life. And compare with a trained ResNet, which trained exclusively on black hole images, and with its goal to reach better spin predictions, we kind of noticed that one of the biggest difference is that in our trained ResNet, there's actually a lot of like spiral arm patterns in these feature maps that are coming from the low surface brightness accretion region. And actually there are 64 of these feature maps. So I noticed that there are roughly half of them in our trained ResNet that contains these kind of spiral patterns, showing that the outer edges of these spiral patterns actually could contain information about black hole spin. And so going back from the input image, on the left-hand side is an image I plotted in normal scale. On the right-hand side is something I plotted in log scale. So then I realized that there's actually lots of detailed structures which are low surface brightness that contains in this information that could have to do with the spin of the supermassive black holes. So this is really interesting for us. And neural network basically shows that there's a fitting function that you can extract from these other structures to learn the spin of the black holes. So one naive way, so these are trained on like really high resolution image. So one naive question you might ask is that how well can we apply on what the current event horizon telescopes have? So naively, what we do is that we add some, we convolve our image with Gaussian blur, which you can see in the middle image, and also add some Gaussian noise on top of it. So which is shown in the right images. So when you try to compare the spin prediction of these two plots, on the left-hand side, you can see that the neural network is performing really well. On the right-hand side, with blurring effect and noise, you can actually see that there's actually much more scattering about how the spin prediction will be right here. And in blind dataset A, we can still see some of the spin value that are picked up right here, even though the scattering is pretty huge. But if we change the plasma physics on blind dataset B, you can see that it's getting more and more flattened. And for blind dataset C, we notice that the accurate spin value is actually deviates from its ground truth value. But on the other hand, it's still able to predict the correct sign of the spin, which is positive. So we're pretty excited about this. So with this in our mind, another question we have is, can we directly apply this trained neural networks on real images? And I'm going to raise up one of the challenges due to time. That just have to do with the image reconstruction of the Event Horizon Telescope. So when we talk about the Event Horizon Telescope as the first image of a black hole, it's actually taken from a lot of radio antennas that are around the globe. So, and after taking the data, people need to collect it and do careful data analysis and calibration, and then use some data reconstruction algorithms, for example, like clean, to reconstruct the data. And one thing we notice right here is that usually the true image and the reconstruction image look similar, but they are not exactly the same. So when you want to apply a neural network on top of it, usually you need to be careful when you do things in the image domain. And to illustrate this idea is that this is actually the 4 images that are generated blinded from the 4 different teams within Event Horizon Telescopes. So if you ask the question of whether this is a black hole, then you probably can call it, this looks like a black hole because it has the ring-like structures. But when we want to estimate spin, we probably want to be much more careful because we notice that some of the detail structure could be related to how we predict the spin values right here. And so for me, the really good way is to go back into the raw data instead of doing things in the image domain. So due to the time, I couldn't provide details about this, but this is basically taken from the paper, Event Horizon Telescope papers. On the left-hand side is something we call the UV plane in radio interferometries, which is the subsamplings of the data in Fourier domain. And on the right-hand side is visibility's amplitude, which if you think that you have a ring-like structure of a black hole and you do a Fourier transformation, there will basically be a bunch of Basel functions. And when you square the Basel function, you'll be looking like this kind of dipping effect, which is labeled as green in our crescent models. So if your visibilities are lying on top of this models, then basically it looks like a black hole. So the question is, can we directly put in this data and into a neural network and estimate spin? And the short answer is yes. So right now, we've been working on an architecture that directly takes in the visibilities from radio interferometry, from the synthetic black hole images, and generate these visibilities and plug it into a neural network. And we can directly do an end-to-end data analysis in the visibilities domain. And what made me really excited is that this is actually really general, not only for the Event Horizon Telescope, but in principle could be applied to any kinds of data in radio interferometries that you can have visibilities of whatever strong lensing, protoplanar disk. As long as you have enough data, you want to do data analysis, then you can apply this technique to estimate the parameters of your interest. And so what makes this work is that when we think about this, we notice that radio interferometry is actually really similar to something called the autoencoders in the neural network architectures. So basically, there's an encoder and decoder, and in the middle, there's a letter representation. Usually, it's some machine learning representations, which is hard for a human to interpret. And as an astrophysicist, when I first jumped into radio interferometries, I don't understand anything about visibilities. So visibility is kind of like an encoded structures, encoded data sets of our real black hole image. And the radio telescope configuration is acting sort of like an encoder of this analog to this neural network architectures. And usually people do clean or other data reconstruction algorithm to get the data back into image domain and then do the data analysis. But if you think of the neural network, you can actually directly learn things from letter representation by adding another neural network on top of it and do data analysis. So I think we have a pretty good architecture on directly dealing with parameter estimation and for EHT right now. That's why I'm pretty excited. So to give us a short summary, I think we showed that the neural network are able to recover spin on high Fourier solution synthetic data sets. And we also use some machine learning interpretation technique to show that they could be keen on some of the low surface brightness features, which are unresolved at the moment, but could be give a hint for us to build the next generation telescopes. And also neural network are also able to provide an end-to-end tool for data analysis in VLBI. And more work would be needed to apply on real data. So with that, I think I'll stop right here and take questions.
All right, thank